Hello, everybody, and good morning for someone, good evening, and whatever. So this is probably the third consecutive speech or class, I can say, that I'm doing in this Atlantic International University. This is a unique opportunity for me to learn because whoever teach, the learns the most. I believe that. So I actually enjoy this sharing of knowledge. So myself, Ikramul Hasan Sohail, I am actually a lithium and battery scientist working for lithium and battery for the production for the raw materials. I mean, from the scratch to the battery pack because of my background in electrical engineering and PhD in lithium and battery. I'm working as a head of R&D of lithium and battery section. R&D section. This is an US-based company, and they have a branch, R&D branch in Bangladesh, where I'm working as a head of R&D. So I have PhD on lithium and battery. So let's start about the content that we are gonna talk about today. So at first, I will give you a brief introduction about lithium and battery and the chemistry. I mean, how the lithium and battery works, because it's all about chemistry. And you know that lithium and battery, it works the principle of chemistry. I mean, the oxidation reduction reaction. So I will give a brief introduction about the battery first, because I am sure that you all are not all are expert on chemistry or battery. After that, I will give a brief introduction of each chemistry that market available in the current market, I mean, commercially available, and the production going on. So, and then I will go through the reason why, what makes chemistry safe. Then we will talk about LFP, why LFP, we are thinking that the safest chemistry, and the market trend of LFP, and then the summary. So at first, I want to give a brief introduction, though I already took 2 classes on lithium and battery, but I'm not sure that everybody was present there or not. So this is important to give a brief introduction about the basics of lithium-ion battery, I believe. So here is the structure, internal structure of a lithium-ion battery. You can see a anode in this side, left side of mine, and then cathode on the other side. And there is an electrolyte, which is liquid for sure. And there is a separator, which is inside, which is separating the anode and cathode. The function of this separator is just to allow lithium ion from anode to cathode and cathode to anode, back and forth. And this electrolyte works as a medium of this transaction of lithium from anode to cathode, back and forth. So there should be a separation so that they should not be connected electronically, otherwise it will be short-circuited. That's why this separator is also necessary. So mostly anode made of carbon or carbon-related material, silicon as well. That we talked about last class, that silicon is a very good candidate of the anode. But today our topic is about cathode. And as you can see on the other side, there is cathode. And this cathode is actually the source of lithium. This cathode supplies the lithium that is stored in the anode inside the carbon hexagonal structure or whatever in the anode side. So as you can see on the right side, there is some composite, which is for sure there should be lithium inside. That's why cathodes are mostly like lithium cobalt oxide, lithium manganese oxide. You will get familiarized with all of the types in few minutes. Then the lithium salt, which is lithium hexafluorophosphate, commonly used as electrolyte. As I said, that lithium hexafluorophosphate or electrolyte is actually the medium for transaction of lithium from anode to cathode. And this actually only allows the ion transition, not the electron transition. So the ion only go through this electrolyte and then through the cathode separator, then to anode when it's charging, and when it's discharging, the other way around. So that's how a basic structure of lithium-ion battery works. And that, as you so you know that cathode is the one that holds the lithium, and this is the source of lithium. And normally this cathode is normally the oxide of lithium, and it's surely a different composite, consists of different composites. So and there is another important reason for the cathode, that cathode is the definer of the chemistry of any lithium-ion battery. For example, if you use lithium cobalt oxide as a cathode and you use graphite as anode, you will not say anything about graphite. The chemistry will be called as LCO chemistry. Similarly, if you use an LMO, which is lithium manganese oxide, a composite of lithium and manganese, and you use this, and on the other side use silicon or niobium oxide, whatever anode, but we will name it the name of cathode. We'll call it with the name of cathode, which is LMO. So now you know that the battery chemistries are named after the cathode. Anode is also important, but the chemistries are named after the cathode. So next we will talk about the chemistries that are available currently in the market and commercially available. That means you can buy from the market those chemistries, and we will talk about that among those chemistries, which is the best for our purpose, for different purpose, and we will talk about it briefly for every type of chemistry. As you can see, there are 6 types of chemistries mainly mentioned here. Actually, there are some other chemistries that is evolving. There is sodium-ion battery, there is lithium sulfur battery, there is redox flow battery. There are a lot of other chemistries, but today's topic is about the safest chemistry of lithium-ion battery technology, and that is already developed, not in the R&D phase or not in the research phase. This all are commercially available, but some are good for some purpose, some are not good, that much good. That's why we are looking for the safest chemistry among those chemistries that are available in the market. So this is lithium nickel manganese cobalt oxide, NMC, which is a cathode material, and the battery is named after this cathode. So lithium nickel cobalt aluminum oxide, NCA, lithium manganese oxide, LMO, there is lithium cobalt oxide. So that means you can understand that what is inside the the cathode: lithium, nickel, manganese, cobalt. So you can see there is lithium, there is nickel, there is manganese, there is cobalt, and there is oxygen. So the name is actually telling you what's the material inside and what are the composition of those materials. And the last is lithium iron phosphate, which is the which we will talk about it in details, and we will see that eventually that LFP is the safest chemistry available in the market so far. Maybe in future some other candidate can come out, but right now in terms of production, in terms of commercial availability, LFP is the most safest chemistry and available chemistry in the market. So at first, lithium, nickel, manganese, cobalt oxide, which is NMC. So NMC is very popular. Actually, it was popular at the beginning of the lithium and battery evolution, and it has a very good market share of lithium and battery because it has very good storage density, power energy density, which is 200 milliamp hour per gram. That means 1 gram of NMC can give you 200 milliamp current for 1 hour. That's why it is actually calculated. So this is called energy density and power density as well. So this has a relatively safe compared to other types of lithium-ion battery, but not the safest one. We will see in the later one. And it has some drawbacks as well. As you can see that normally, if you think about lead-acid battery can go through 500 to 1,000 cycles. And after 1 or 2 years, you need to change the battery for whatever purpose you are using for. And this NMC is not that much, I mean, good life cycle. And that means you can use this battery for 3 to 4 years safely. After that, you can still use, but it will have less capacity. That means after 1,000 cycle, you can get 85% capacity from this chemistry. That's why this has decent life cycle, but I mean, not the highest amongst the chemistry available. And also in terms of safety, this is also not good, because as you can see here, there is nickel, there is cobalt. These two are toxic for the environment. I mean, not good for the environment, and they are not environment friendly. And their mining method is also not that much friendly. If you know about these cobalt mines in Africa, so there are some issues with this material that is coming from the sources, and also not good for the environment. So this chemistry, because of its material itself, is not very environment friendly. Also not have the highest amount of life cycle. You can get it from here. So that's why this is not that much preferable. That's because we are looking for the safest chemistry. So we cannot say that this is the safest chemistry, but in the market it is available and people are using it. But in the future, it might be getting obsolete and people might switch to other chemistries. If we go forward, we will understand it slowly. Then there is lithium, nickel, cobalt, aluminum oxide. That means before there was manganese. So manganese was also rare earth metal, and its reserve is not that much. So people are trying to get rid of those rare metals or materials. Then they came through this aluminum oxide idea. In the place of manganese, nickel cobalt is there, but the manganese is replaced by aluminum, and the whole chemistry changed. That's why the name is nickel cobalt aluminum oxide, lithium nickel cobalt aluminum oxide. So they have very little bit higher capacity than NMC that we just looked before. It was around 200 milliamp hour per gram theoretical capacity. I'm telling theoretical capacity. This is not the ideal capacity, or it is not possible from getting it from each and every battery. This is an ideal theoretical capacity. This is ideally, this has a little bit higher, which is 203 milliamp hour per gram. As I said, that 1 gram of nickel cobalt aluminum oxide can give you 203 milliamp hour current for 1 hour. But there is another issue similar to the NMC, that it is very much prone to thermal runaways. That means above 120, 150 degree, it will go through thermal runaway. And if you saw some accidents that in the electric vehicles, which sometimes people make it viral, those who do not like electric vehicles. So you can see that sometimes fire broke out. And this is also a reason because of the chemistry, because some chemistry like this chemistry are not that much good for thermal, I mean, withstandability. So it goes through thermal runaway, and whenever it goes through thermal runaway, fire will surely break out. And that is which will create problem. And it has not that much good in life cycle. I mean, you can cycle it for 1,000 to 2,000. Full life cycle means full charge and discharge. If you charge once and then fully discharge it, this is 1 cycle. That's how you can do this for 1,000. So if you do it for every day, you can run this for 3 years. But again, it has nickel, it has cobalt. Though aluminum is there, aluminum is not harmful, but nickel, cobalt is again problematic for the environment and not that much good in capacity in life cycle. So maybe we will get some other alternatives to those. Then this come out about lithium manganese oxide, LMO. This has very good capacity, as you can see here. It has a good has a high power and energy density, and it operates well in a high temperature. Capacity is about 296 milliamp hour per gram, and it is mostly used in portable power tools like laptops, medical instruments, and some electric vehicles as well. But the problem is huge here. That means you can just cycle it for 500 to 800 times, even less than 1000 times. That means you cannot run this battery more than 2 years. So within 2 years, your battery will get degraded, though it has very good capacity in terms of other two chemistries that we have seen, but it's not the best one because of this lower life cycles. And that's why it is losing the popularity from the market, because if anyone buy any battery, he don't want to change the battery in 2 years, which is lead acid battery is already available. You can change it for after 2 years. So why taking lithium in place of lead acid with higher price and just lasting for 2 years? Because the price of lithium and battery is higher, so people are expecting more life cycle from that. That's why it's not that much good in terms of the use in practical life. Then there is lithium cobalt oxide. Again, it has cobalt, but the good thing is it has very good capacity, and it is very light in weight because with lithium, it has just only one element, which is cobalt. Previously, there were 3-4 elements: lithium manganese oxide, cobalt aluminum oxide, nickel cobalt aluminum oxide. So in terms of a specific in terms of specific weight, it has the least, and this is the lightest among all the materials. And it has a lifespan of about, again, 500 to 1000 cycles. Not that much, cost effective. People will not prefer that much. Only 1 or 2 years it will run. But this has very lightweight. This is also a good property, because normally the most expensive and the most weighted elements is inside a EV is the battery. If you see the battery pack, it is almost even 100 kg, 200 kg, this range of the size of the battery. The weight of the battery is huge. So if we can use a lighter element and lighter battery, that can significantly reduce the weight of the vehicle. But again, the life cycle, the cobalt is there, so not that much preferable. Then you can see lithium titanate oxide, which is very good in life cycle, as you can see here. It has almost 10,000 life cycle. It is very good that it charges very quickly. You can charge it in 1 hour, 2 hours. This is also a good property, because people are looking for fast charging. Because when you are going for a trip and you are in the middle of your way, and you do not have the chance to charge it, quick charging is become very vital on those places. That's why it is a good property that it can charge quickly, but it has a little bit lower energy density. You can see here the energy density is about 50 to 80 watt-hour per kg, Well, the conventional chemistry that we have seen so far can give us 120 to even 500. Some of them can give you 500, which are not that much commercial, but in the research phase they were able to do that. But you can see it can give you only 50 to 80, which is almost 50% of the conventional chemistry available in the market. And there is another problem, that you have lower nominal voltage, which is just 2.3 volt for lithium titanate oxide. Because normally during the battery pack, we need to build the battery pack to a certain voltage. For example, you want to make a battery pack voltage 100 volt. In that case, you will need almost 50, 20, so 30, almost 40 cells in series you will need to connect to make it 100 volt. But other chemistry that we have seen previously, their nominal voltage is about 3.2 volt, which is almost 1 volt higher than this. So on those cases, you will need less amount of battery. 30 batteries in series can give you 100 volt. But in that case, you need 40, which is a costly element because of this number of cells. Again, you have low in capacity, 50 to 80 watt-hour per kg. That means your weight of the battery will get higher for the same amount of energy. For example, for 1 kilowatt hour energy, you will have to increase your size double. I mean, weight would be double, and also the higher number of battery will also make it higher, the weight, I mean. So this LTO is not that much preferable in terms of every trader, because it cannot satisfy all the sectors. Then we will go through the LFP, the lithium iron phosphate. You can tell it the boss of the safest chemistry currently available in the market. Maybe some other chemistry may come forward, but right now, in terms of the production ability, in terms of the material resources available in the market, LFP is the best because of some reason. As you can see here, its capacity is good, which is 160 milliamp hour per gram. Though you can tell, okay, we have 200 milliamp hour per gram, 270, but they have other drawbacks. That's why we cannot say just capacity as a deciding element. Also, if you see here, we have lithium iron phosphate. Other than lithium, iron is the metal that is necessary inside this battery. And you know that iron is not a rare metal. It is available everywhere. In terms of the mineral, they are also abundant in the earth. So iron is cheaper, and ultimately it has lower production cost because of this cheaper elements that is being used in that cathode. So in that chemistry, there will be lithium and iron phosphate makes a composite that will make lithium iron phosphate. And it has very good thermal runaway property. That means it can withstand up to 200 degrees centigrade. That means if you can keep the battery within 200 degree, you will not even go through the thermal runaway. I will also show the other tests in the next slides. But in terms of the life cycle, it has very good life cycle, which is 5,000 to 10,000 cycles. And you can see in the right side, there is nominal voltage, which is 3.2, and which you can normally charge about 3.65 volt. And you can see that you can make it very bigger in size. And in one cell, you can give 105 ampere hour of current. You can store it. Charging temperature is good. You can even during the charging, if the temperature runs to 55 degrees centigrade, there is no problem. And even discharging time, that means during discharge, even where the temperature become lower, I mean sub-zero temperature, that means lower than the zero minus temperature, I mean. So it can also operate in that environment as well. That means it can discharge. Discharge means it can operate. It can give you power or energy. That means when it's even minus 20, you can even discharge it. And the highest is 55 degrees centigrade. So this cell is a good cell in terms of all the things that I have mentioned here: the life cycle, the safety, the element that are available in the environment, iron which is available in the market. So it has no problem of using it. I mean, in terms of the safety, it is the best because of its element that is being used here. So now we will talk about the LFP a little bit deeper after seeing the overall comparison, as you can see here. So all the 6 types of batteries are here. You can see there's lithium cobalt oxide, there is lithium manganese oxide, lithium iron phosphate. As you can see here, the parameters are represented with an hexagonal structure. As you can see here. On the top, there is specific energy. That means this is the highest limit of a specific energy. There is a specific power, safety, performance, lifespan, cost. That means we want that all of the 5 parameters should be high enough, but the cost should be lower. But as you can see, LCO, in terms of safety, not that good. A specific power, not that good. Performance, not the best. Cost, little bit, but lifespan is very low. So that's the way to see the properties altogether. Then there is LMO. It is very good, a specific energy, a little bit, a specific power. Safety is good, but in terms of performance and because of the lifespan, this is very low, and the cost is not that much lower than the LCO. Then there is LFP. You can see that it has highest specific power. That means in terms of power, but you can see in terms of energy, we saw that it has 160 milliamp hour per gram. That's why the specific energy is a little bit lower, but the specific power, that means it can hold the voltage for longer time. In that case, specific power, it is best. You can see that it is on the line. Then safety, as I told you, this is very good. In terms of performance, maybe not that much good, but very close to the highest. In terms of lifespan, which is among these 6 chemistry, the highest. And the cost, you can see, in terms of the cost, it is not that much costly because of the less costly elements and that has been used here. Then there is NNC, as you can see here, every one is good, but this lifespan, safety is not that high. As you can see, safety is high, lifespan high. These are not there. NCA, again, some drawbacks. The cost is okay, safety is good. Then a specific power is not that good. Then LTO, you can see here on the upper side, very low. On the lower side, there is safety, performance, lifespan, but cost is also low. But a specific energy LTO, because of the size and energy, density, the size will be very high, double of the conventional size of the battery pack. That's why not that much good for application like electric vehicles and other high power, high performance applications. So so far we have seen that LFP has a very good property and the safest in terms of thermal runaway and becoming withstandability of thermally. So then next there will be we will talk about actually what makes a chemistry safe. That means we are telling that LFP is the safest. So as I told you, not only the number of cycle, it should have high peak power, which has very good power density, as we have seen. It should have low production cost, minimized chance of thermal runaway. It should also do that. And it should withstand the nail penetration test. Nail penetration test is a very common test that is done for each and every cell to give certification that the cell is safe, the chemistry is safe. So it should withstand nail penetration test, and I will show you how it behaves in terms of NMC and LFP with the picture. So that means if just a battery is only safe in terms of the safety and catching fire, you cannot produce it. I mean, people will not prefer it. Nobody will be happy to produce it. So it should be commercially available, commercially viable, environmental friendly, and should be safe and have good, decent capacity. That's why we are telling that LFP has all of from each and every section, it has some properties, and that's why it is safe in terms of the commercial purpose, safe in terms of safety purpose of catching fire during the operation of high power. So now we will a little bit deep dive into the LFP battery. As you can see here, inside one LFP battery, if we break it down, you can see that 4% is cell container, which is aluminum, and this is very light in weight. So if you think this full battery is 100%, so 4% will contain the cell container, which is called cylindrical case. Then 20% of the cost, or 20% of the area, will be covered with electrolyte, which is also important because without electrolyte, lithium ion cannot be transported from anode and cathode back and forth. Then there is separator, which is a thin membrane, normally for lithium-ion battery. It has shown like a solid material, but it's not like that in terms of lithium-ion battery. It has just shown for the purpose of demonstration. Then there is 31% from anode side, and we know that anode is mostly used with, made of graphite, and silicon is also trending, and which will be the next generation anode active material. And in a LFP battery, 30% is from anode, and all other 43% contributed by cathode. And in that 43%, that means which is our LFP, we have 4% lithium. That is not much in terms of percentage. Then 35% is iron, and 61% is phosphate. That means all of the material other than lithium are very less in cost, as you can see here. Just 4% lithium, 35% iron, 61% phosphate. People are trying to increase the amount of lithium because lithium is the one that defines the capacity. As you can see that we have 160 milliamp hour per gram capacity. If we want to increase it, we need to increase the amount of lithium. But directly, it is not that straightforward that you just add some more lithium. It has a structure that I will show in the next slides. That you have limitation of adding lithium, but you can dope with and you can coat it with other materials and increase the performance. So this is the overall composition of an LFP battery. Now we will talk about the basic principle a little bit about LFP battery, that how the LFP is actually working. That means during charge and discharge, how it behaves during charge and discharging. So actual lithium iron phosphate was recently introduced or reported in 1997 by Goodenough and his co-workers. And so far, this is the most promising cathode candidate, and that will be using in largely in the coming years. And as you have seen that it has very low toxicity, low material cost, flat voltage profile. That means it can withhold the voltage for a longer time, long cycle life, and it has very good voltage, which is 3.2 volt. As you can see here in the lower image, when iron phosphate is there, that means it is not lithiated, that means fully delithiated, and that means it is fully discharged. The cathode is fully discharged. Then the lithium insertion will start, and as you can see, lithium is slowly increasing. For example, Y mole of lithium has inserted into the iron phosphate structure. Then this yellow is actually representing the amount of lithium added. And after the fully lithiation phase, you can see that it is yellow in color. That means the full lithiation has been done. So that's how the lithium insertion happens in terms of LFP, lithium iron phosphate. When it's fully lithiated, then you need to delithiate it and extract lithium from it. Actually, there is a trick here, that this lithium insertion for cathode is actually discharging for anode. And when we are telling that lithium extraction, that means lithium is going out of this lithium iron phosphate. The lithium is now charging the anode, that means charging the battery. So as I have told earlier, lithiation of the anode is the charging, and delithiation of anode is the discharging. So this from the anode side. From the cathode side, as you can see, lithium insertion, that means lithiation of the cathode is actually discharging, and lithium extraction, that means delithiation of cathode, is actually charging. So as you can see here, the reaction here, when the lithium iron phosphate is fully lithiated, then you get the lithium from it during the charging. And this lithium is actually mixed alloy with the anode side with the carbon. And as you can see, LiC6, that means 6 carbon atom holds on lithium inside it. And that's how it goes back and forth when charge and discharging repeatedly. So this is for all, for all types of battery, that's how it works: lithiation, delithiation, charging, discharging. And then the structure of the LFP, internal structure. That means where is lithium actually resides in an LFP. As you can see here, the structure is called olivine structure. Olivine structure. As you can see that this blue is representing iron, the red phosphate is represented by red, and lithium is this small ball shaped is representing lithium. As you can see here, the path of the lithium is actually in circle. This is like a tube, and the whole structure is held strongly by iron and phosphate. That means iron, potassium, and oxygen. As you can see here, this green is oxygen. This middle one is phosphate. So that's how the structure become very stable, and that's why we call it a stable structure. Why we are calling it stable? Because as you can see here, lithium is actually residing inside the hollow space. That means when you take the lithium out and then again put it back, there will be no expansion of the structure. That means there will be very less delamination of the structure. If the structure is like this, that means the lithium is resides inside the hollow place, which is empty normally. So it become very stable in structure. That's why we are calling it stable structure. And you can see here as well that lithium is residing in a place which is already empty, and this has a tubular path. It can in one way, if, for example, it's like a pipe. The water moves into the pipe in one direction in a tube. That's a similar way lithium go back and forth inside this hollow structure. So it has a little bit lower electrical conductivity in terms of pure lithium iron phosphate, because it has just 4 angstrom distance from nearby iron atom. So this can be solved, and that's how people are doing the optimization of LFP by just blending carbon with the LFP. We can get rid of this problem, and also doping and other modification techniques can be used to optimize the LFP. So this is also very much practiced. People are using it commercially. So this little bit lower electrical conductivity is not creating much problem, because we have carbon and other sources, doping sources, that can increase the conductivity. So if we want to look into the more deep into the advantage of LFP, there is a very good property of LFP, which is high discharge rates. Previously, we have seen that some of the chemistry have very good charging rate. It has very good charging rate as well, but all of them cannot discharge very fast. If you want to build a very high performance car, that means a sports car or anything that needs very high power instantly, for 10 seconds, 30 seconds, you need a very high amount of power. This LFP can give you, because it has very high discharge rates, high efficiency that we have seen, and with the structure stability, extreme temperature uses, that means it can go up to 200 degrees centigrade. There is no problem. Lightweight in terms of other batteries. No active maintenance is required, like acid battery. You need to change the acid water regularly, and it has zero memory effect. That means if you charge it 80% and put it, and then again charge it to 100%, and then again discharge it to 70%, it will not kill your capacity. That means it will not understand, or it will not keep in the memory that you are always charging it to a certain level and not fully charging it or not fully discharging it. That means from any charging state, you can charge it full, you can discharge it, and then again charge it, and then again discharge it. That's why it's not having any residual charging or memory effect. That means if you even do not charge it, you can use it again when you charge it fully. Then high safety for AV, which is necessary, low cost. We have already shown that long cycle life is there, and environmentally very sustainable because of low toxicity. That's why EV industries are very much keen to use it, very much interested to use this chemistry. Then it comes about the safety threshold. That means how far a lithium iron phosphate can give you safety. As I have told you already, it can withstand up to 200 degrees centigrade, almost 195 degrees centigrade. And there is very unique and extreme properties, which is nail penetration test. As you can see here in the right side, in that test, normally a nail, which is iron nail, penetrates inside the battery. That, as you can see here, this battery is penetrated directly, radially, from one side to another with a nail, and it is done inside a chamber. As you can see in the left side, it is NMC. After this nail penetration test, within seconds, it caught into the fire in the left image. But with a working and new LFP battery, after the nail penetration test that is zoomed and shown here, you can see here there is no fire. So that's how it is able to withstand a nail penetration test. And so far, in the chemistry available in the market, which has all of the properties, LFP can hold this test. That means it can pass this nail penetration test without any problem. This test is done because when there is any accident in the car, lithium battery run vehicle can catch into the fire, but LFP will not, according to its property. As you can see here, even penetrating a nail, that means penetrating means you are actually short circuiting the anode and cathode internally when there is no fire. So that's how the LFP is becoming very popular, and in all the market, Europe, Canada, America, people are running after it. Expectedly, China is leading LFP market. They have very good facility infrastructure of making of LFP. So almost all the, leading Chinese manufacturer are currently producing LFP. In Canada, you can buy cell, which is very good in capacity, 230 ampere hour per cell. And in Europe, Germany is leading in LFP manufacturing. In fact, it has the highest number of battery production facility, LFP battery production facility in EU, all over EU. US is also focusing. I did a thorough research on USA cell producers. These cell producers are turning to this LFP as well. Almost all of the almost 80 to 70 to 80% cell producers are planning to make LFP production, and they are already working on it. And within few years, you will see that LFP will be made in USA as well. So, and in test, and if you see Tesla, they have already adapted LFP chemistry very well for EVs, and also it has very good application in stationary energy storage alternative to generators. Fossil fuel generators are also being replaced by LFP batteries, run big size batteries, big energy storage. So EU countries are also, they are not mass producing, but they are also thinking about production very efficiently and actively. So that's the current market of LFP in brief. So as we, in concluding remarks, in summary, we can say that LFP is the safest chemistry so far commercially available in the market in terms of cost and safety, environment friendly, hold decent capacity, stable structure, several way of optimization like doping and mixing with carbon. And then next emerging chemistry of EVs is the LFP. So that's all from me from now. Thank you for listening. And I will appreciate if you have any question, and I will be happy to clarify. So I think this will be the QA session. So from my side, the presentation is done. So thank you for all for listening it with patience. And now the QA session, please.
Thank you very much, Prof. Ikramul Hasan. We all have been listening very closely. It is a topic of interest, of very high interest for everybody, because electricity, power, energy, that is what is leading the world. In our activities, we need to know very well what type of battery technology we should lean on. It's been a very, very interesting topic. Personally, I have at least 30 questions, which I'm writing down as I move toward the process of your presentation, Ikramul, but I'm going to put my questions aside because the priority goes to our participants. But before I go to the hands that I see up at this time, there's a question that popped up at the very early stage of your presentation. And I don't want that participant to be frustrated because the question has had no answer. But let's go quickly to it. I don't know if Onias Mpofu is still around. I'm not looking at the whole screen. By the way, if you would put away the presentation so that I can see all the faces. There we go. Thank you very much. But I'm gonna head right away to the question that Onias Mpofu put in the chat line. The question is, as follows. What does it mean for a battery not to be environmentally friendly? What does it mean for a battery to have issue with the environment? Does that mean, by the way, that it causes danger or any type of risk? This is the question from Onias Pofu. What is your stand, Ikramul?
Actually, if you think that after use of any battery, that means after using a battery, what will you do? You cannot throw this battery away, right?
Okay.
So for example, we are looking for safety. I mean, we are looking for getting rid of the fossil fuel, and then we are landfilling. We are using a battery, and after 2-3 years, we are throwing it, or whatever is doing. Even if you are not throwing it, there is a rule that you have to recycle your element. Every element, every battery producer have to have a recycling mechanism. But you can see cobalt recycling is very dangerous, whoever working there, and also environmental unfriendly, because whenever you are refining it, you have to give something away from the refining process. That's why this environment friendliness is important, because you are cycling it in the environment, and we are not letting it landfill or wasted and then cause the environment problem. That's why the environment friendliness is important, because we are trying to get rid of the fossil fuel.
Thank you very much. Let's now go to the hands that I see up on the screen, going first to Dr. Caleb Magutu. Dr. Caleb, we are here for your question.
Okay, thank you very much for giving me this opportunity. I am an electrical engineer, and I think I'm the most blessed person and the most person who has really benefited from this presentation. I am doing my postdoctorate degree research on let's say, I'm looking at if it is possible for the people living in Machakos County of Kenya able to use solar energy to power their homesteads. And I have been, I've been wondering which type of battery can I use, which they can be able to charge for a short time, and then provide the power for a long time. And I've seen you have indicated very clearly that the lithium iron phosphate is the best.
For sure.
And I'm requesting that you allow me to link up with you so that I can get more information about batteries. Thank you.
Yeah, sure. Thank you. Yeah, LFP is the best. In fact, if you want to search in the solar battery, lithium-ion battery, you will see LFP, and you can buy it. The large size LFP is the best for this type of application. Okay, not the cylindrical size. The size that I have shown in the presentation, this size is best for you. If you just use 4 of them, you can make 12 volt, and you can easily replace the lead acid battery, and you can get very good power. So no problem, go ahead with the LFP for sure.
Zadiano Sibi.
Thank you very much.
Thank you, Dr. Caleb. It is now the turn of Zadiano Sibi. Ready for your question, Zadiano. But apparently, Zadiano is not ready as of yet for us. Zayano CD Atahiro, are you there? We are listening to you, brother.
Yes.
Yeah. Hello.
Yes.
Hello. Yeah, we can hear you.
We all
Okay,
hear.
Yes. I'm Zayano CD Atahiru. Hello.
Yes.
Hello,
yes,
yeah.
we are listening
You
to
can
you.
go ahead
Zayano.
with your question.
Please, I need more clarification about that battery line chemistry. What I need more about is the different type of that cell battery. I need more about it. The one that is used
I
for
see.
solar and the one that is used for motor car. I need more clarification about the differences.
Yeah, I have already presented the differences, the properties, and I think you can choose your battery type. And if you have safety issue and you need very good power density and lower in cost,
Okay.
you can buy directly from the market LFP, and you can demonstrate it. You can try to use it. I hope it will be good enough for you.
Okay. Then which one is more better to use for the solar energy? Which battery is more better?
In terms of this LFP, as I've already mentioned, LFP is the best because of so many reasons, and it has life cycle, very good, environment friendly as well, lower in cost. In terms of material production cost is lower. So I hope you can buy it directly from the market and use it.
Okay. Thank you. Okay, thank you very much for this. Thank you very much.
You're welcome.
Okay. Jane Toshuku, your question, please.
Good afternoon.
Good afternoon.
Good afternoon.
Yeah. Thank you, Dr. Hassan, for a wonderful presentation on surface chemistry lithium battery. Here in Nigeria, we are used to dry cell battery and non-dry cell battery. And now this battery in question, we got to know about the chemical reactions, which is the anode, cathode, cations and anions, positive and negative ions. Now, this battery, after usage, do you have the capacity to recycle? And when you're recycling, are you recycling to the same product of battery, or are you recycling to another product? Hence, we know that recycling is based on waste to product. So which one is possible with this surface lithium battery? Thank you.
Actually, it's a very good question. Thank you. You can charge or discharge a lithium-ion battery if you have a electric vehicle. You can go up to 80%. That means when your state of charge of your battery is lower than 80%, you cannot use it for EVs that needs high power application. But the good thing is, after this 80% capacity, which is already there, this battery can be used for solar. That means if some electric vehicle battery is, end of life is done, so anybody can buy from this EV and then use this same battery pack for his solar application. So because solar application, after this 80% state of life, you can even use it for your purpose. That's why that's the thing. After it being obsolete from the EV, you can still use it without breaking it, without fully recycling the materials. And there is also a very good business in USA, that recycling business. You can recycle the full material, can tear apart all the material and then produce the LFP again. This is a very trending business in USA, and all of the industry should have a recycling mechanism. So in both ways, you can do that. After end of life from the EV or any high power application, you can use it for low power. And then again, you can break it after that and produce LFP again after recycling. So both ways it is possible to recycle. Thank you.
Thank you very much, Ikramul. As we are waiting for the next hand up, let me bring up one of the issues that I believe might be of some type of interest. The presentation, Ikramul, has been extremely academic, which means there are certain elements that the average citizen would not be able to understand when we talk, for example, about cathode and anode and electrolyte and so forth and so on, so many other very important concepts that you've used in the world of batteries. But let's try to go down a little bit to what would be a concern for everybody. We are all consumers. Let's go to the low level of the consumer. We go to a store to buy ordinary batteries, for example, for our watches, for our electronics, and so forth and so on. How do we know which is the best type of battery? We understand that the LFP, like you explained, is the best type, but we're looking again at the common user. We go to a place to acquire batteries for our electronics. We don't know which type of battery to ask for, to go after.
Actually, it depends on your application. In which application you are going to use it, this has very high impact on your selection. And if you need a primary battery, that means just dry cell. I mean, for example, remote control, like this remote control and dry cell, you can just buy it normal dry cells. But if you need a rechargeable batteries that you can buy it, then you need to think about which application you want. Do you want to frequently discharge it? For example, in a day, you even want to charge it 2 or 3 times, discharge it 2 3 times, or you just charge it once and you use it 1 day, 2 day. So in terms of these applications, you can define your chemistry as well. But in general, when you are thinking about that, I need very good charging, I need very good discharging rate, I need a lower cost, because commercially, when you are thinking, then the LFP is coming into the picture, because everything you can get it from the LFP. But for example, you want to buy 1 cell or 2 cell, so you do not need to think about that high, because you are not spending thousands of dollars for a battery.
I got it.
You should then think about what is the available in the market and which one can serve your purpose. That's it. Because you are not using it even $20,000 battery, right? It's just a $1 battery for you.
Very good clarification. Thank you very much. Now let's turn to Owe and Bassam. Owe. Are you ready, Owe?
Yes.
Okay, go ahead.
Thank you, Doctor. Thank you, Hassan, for that wonderful presentation. I had the network issue, so I didn't quite understand the cathode and the anode description you were giving, number one. Number two, could you also shed more light on lithiation? I didn't quite get that explanation also. Lithiation, and then in the beginning when we were talking about cathode and anode and the pole, I didn't quite get you.
Okay, so you should always keep it in mind that lithiation means charging. When we have a battery, phone battery, you are charging, you are lithiating. So lithiating what? Lithiating your anode, because anode is not containing lithium. Anode is carbon. So when the lithiating means what? Do not have lithium there. So you are lithiating that anode, which is carbon. Then you are charging it. When you are discharging it, when you are using it, then you are discharging it. This time delithiation. Delithiation of what? The one that you already lithiated. So you have to delithiate it. Then you come delithiate. Then it's charging and discharging. Lithiation, charging, delithiation, discharging. So this is in terms of anode. When you come to the cathode, this is just exactly opposite. When you are charging the anode, lithiating the anode, who is supplying this lithium? Cathode. Cathode is supplying the lithium. So cathode is actually sending lithium during charging, and during discharging, this lithium coming back to anode. So this actually a little bit tricky, and you need to think about in one case and make a reference, like reference of anode or reference of the cathode. If you think anode, this is very easy. Lithiating means charging the anode. that means charging the battery, and delithiating means discharging the anode, discharging the battery. So that's the simple, and you need to think about simply. Do not make it complex. Just keep one reference and think, where is lithium going, and then from where it is coming back. So that's why I give a very brief introduction about this, because I already taken 2 other classes, which was even more basics of the lithium-ion battery chemistry. First class was lithium-ion battery core chemistry. Then second one was anode, and this one is cathode. So I'm trying to make it, series, not like segregated or one separate from one another. They are connected. So if anybody is here who is following me from the first class, I hope they will understand it very well. And then if you want to study it more, I will tell you that from this idea today, you go to the internet, search it, and then learn it if you want to learn more. And if we have chance, we can have more classes in the future. Who knows, maybe your question will be answered next. Thank you.
I'm very, very impressed. That was a very, very deep and clear detail to that question raised by our participant, Owen Bassan. With this, ladies and gentlemen, we are about to close this outstanding presentation of Ikramul Hasan on the topic of safest chemistry for Lithium battery technology. We are all very appreciative to the presenter. We got it all. The academic standpoint, the details, the types of batteries, the processes, we got it again all. And for those of you who have raised the issue about how you can get this presentation again, number one, as a follow-up, Ikramul Hasan will certainly, I have no doubt about it, he will be back for more on this topic. Number two, for this presentation, today's presentation on this Monday, July the 31st, 2024, the session has been recorded, and the recording will be shared with you, ladies and gentlemen, through your email or on your student portal. And another option is that you could also go to Facebook, where we have a page in there. And you go to Facebook, you type in Atlantic International University, scrolling down, you will see all the past presentations, including this one by Ikramul Hasan. We are all grateful to each and every one of you who has attended this session. And we are turning the floor back at this time to the presenter, Ikramul Hasan, for his conclusion.
Thank you for this wonderful session today, and thank you for listening. Actually, I just want to tell you that from this class, you should just get an idea and get a very initial idea, and then go back to your own study. Then you will understand it, because in 1 hour, it is not possible to give you the full and final idea of any topic, because I am doing PhD. It's a 4-year, 5-year study. So in 5 years study cannot be completed in just 1 hour. So we are here to give you interest and raise your interest, and then you go ahead and study by yourself. And for the next session, come up with your question if you have it, for other presenters, maybe to me or others. I again thank you and appreciate your time, and hope to see you next. Thank you.
Thank you again. Thank you very much, Ibrahim. Ikramul Hasan. Ladies and gentlemen, Ikramul, you all be blessed. It's been a real pleasure. Hope you spend a wonderful Monday, wonderful week. Tomorrow will be August. Bye-bye now.
Bye-bye.